Alright, so in this video we're going to introduce surface integrals of vector fields, or in other words, flux integrals. So the general idea of taking this is that you're gonna have an oriented surface and you're gonna take the dot product with respect to some vector field f, and this is the same as saying, well, what if we take the oriented surface described by some parametric surface r, then we take the cross product of its derivatives, and that becomes another vector in itself. We take the dot product with f, and that's going to give us the projection of that vector field onto the surface area, or essentially how much of that vector field is traveling through that particular element of area, and then we're just adding up all those contributions for the entire surface. Now, what is a flux? Well, the flux is just the flow of something through a particular area. So there are a lot of different definitions for this, and in physics and engineering we find them a lot in things like power flux. So for example, if you have a beam of light that is traveling through a specific amount of area, then the radiant flux is just how much light is hitting a specific amount of area. And there are other things like electric flux, magnetic flux, and things like that. So anything that can be represented as a vector field flowing through some area is going to be considered a flux. And this is why flux integrals are so important in physics and engineering. So we won't be doing anything very different from what we have done so far. I mean, we know how to compute surface integrals, so all we need to do is just extend this concept a little bit further to account for vector fields. So let's do a simple example here. Suppose you have this vector field set by x, and you want to compute the total flux across the surface described by this sphere of radius 1. Now, if you want to compute this integral, the first thing you need to know is, well, what is going to be the surface r? We need to find the parametric surface here, of course, because we need to take the cross product that and then the dot product with f to compute the integral. So the first thing we're going to do is choose a set of coordinates. So because we're dealing with a sphere again, we're going to use the coordinates x equals to sine phi cosine theta. So the same thing we have been using so far. So y equals to sine phi sine theta, and then z equals to cosine phi. Alright, so we have radius 1, so that's basically what goes in here. And now the next thing is to define the area. Well, the element of area we know is just going to be d theta d phi. So the next thing we need to know is, well, obviously the limits, because we're taking the full sphere. We're going to have theta 0 to pi, and then phi 0 pi. Alright, so we have all that information. So now we can write the parametric surface in terms of phi and theta as follows. So we're going to have sine phi cosine of theta, sine phi sine theta, and then cosine of phi. Now you notice that in this case we're not actually going to use the magnitude of this. We're just going to use the vector itself, because when we take the dot product of two vectors, we get a scalar value, which is what we want to integrate. So in this case we're just going to compute the derivative. So we're going to have dr over phi first, and this is going to become, well, if we differentiate it, this becomes cosine phi cosine theta. This one is going to be cosine phi sine theta, and then minus sine phi. Then for this one, we're going to have, this one becomes minus sine phi sine theta. This one is sine phi cosine theta, and then 0. And now we want to take the dot product of those two quantities, so we're going to have this cross with that. So let's see what we get. We know this is going to be a vector, so we're going to have the following. Alright, so let's do it just straight away here. So we have this over that, so basically first element is going to be this minus this times that. So this is going to be 0, and then we're going to have minus this, so sine squared phi cosine of theta. Then for the second one, we're going to have this times that, that's 0. So let me just write it here. And then this times that, that's going to become minus. So minus sine phi cosine of phi sine squared theta. So this becomes plus. Oh, actually it should be minus because I lost track of my calculations. So we had minus because this is the y element. Now we have this times that becomes minus, but remember we're subtracting this, so that becomes a plus. So this is going to be plus here, so this becomes minus in the end. And then for the very last one, we're going to have this times that, so this is going to be cosine squared phi, actually cosine, let me write it here, sine phi, cosine phi, and then cosine squared theta. I believe I made a mistake here. I multiplied the wrong thing. Alright, let me just do this one again. Let's start over from the second element. It's a bit confusing, so sometimes you just have to take your time. So we had this times that, that's 0. And then we had this times that, that becomes a plus, but then we becomes a minus. So sine squared phi sine theta. Okay, so that should be okay. And now for the last one, we're going to have sine phi cosine phi cosine squared theta. And then minus this, so we're going to have minus. This becomes plus sine phi cosine phi sine squared theta. Alright, so now that we have that, let's rewrite this as sine squared phi cosine theta. Second one becomes a positive, so that's sine squared phi sine theta. And then the last one, we notice that this and that are common, so this and that are going to add up to 1, so we have sine phi cosine phi. Now the next step is of course to represent the vector field in terms of these coordinates as well. So we're going to have to replace this by those things. So we have set here, so that's cosine phi. Then the second one is going to be sine phi sine theta. And finally sine phi cosine theta. Now we're going to take the dot product of this with respect to that cross product. So alright, so this is going to give us the following. We're going to have, remember the dot product is going to turn out to be a scalar quantity, so we need to be careful about how we do the addition. So this is going to be multiplied by that, so that's going to become sine squared phi cosine phi cosine theta. Now we have this times that, which is going to be, okay, let's see, plus sine cubed phi sine squared theta. And then we're going to have this times that, so that's going to be plus sine squared phi cosine phi times cosine theta. Alright, let's see if we can group anything here. So we have, well, this and that are going to be the same. So sine squared phi cosine phi cosine theta. And then here we're going to have plus sine cubed phi sine squared theta. And unfortunately, we cannot really simplify this any further. So this is what is going to go into our integral. So now this is what we want here. Alright, so we're going to get this integral. So now we're going to integrate from 0 to 2 pi, then 0 pi of this whole expression. So 2 sine squared phi cosine phi cosine theta plus sine cubed phi sine squared theta, and then d phi d theta. So this is going to be our integral. So now all that this is going to become is just a matter of doing it step by step. So what we can do is, well, you notice the first thing you notice is that you can actually separate this into two integrals. So basically what we can do is we can say integral, and let's take the 2 out here, 0 to 2 pi of sine squared phi cosine, actually this should be pi because I'm doing it the other way around, cosine phi d phi, and then this is going to be times 0 to 2 pi cosine theta d theta. So this is the first integral, but you notice that what I did was separate the phi from the theta, and the reason for that is that our limits of integration are all constants. So that means that we can separate this into a product of two different integrals. So we can integrate this first and then multiply by the result of this. And now we do the same for this one, so we can separate it into two portions. So we have 0 to pi of sine cubed phi and then d phi, and then multiplied by 0 to 2 pi of sine squared theta d theta. So now we can evaluate 4 different integrals, multiply them together, and see what we get from that. So let's go up here. I'm just going to clear the screen so we have more space to work with. So let's just get rid of all this. Alright, so how about we, you know what, let me just copy this. So move. I'm gonna copy this thing here. Gonna move it all the way up. So we have a clearer view of what we're doing. And now let's do the first integral. So we have 2 from 0 to pi. Alright, so this is going to be, I believe, oh, actually it's quite straightforward. We can use substitution, but I already know what this is going to be because we have done it before. This is going to be 1/3 of sine cubed phi from 0 to pi. And the reason for that is that if you differentiate this 3 comes down, cancels out with that one, and then you have sine squared phi, and then take the derivative of that, which is cosine phi, so you get back to the original expression. And we already know that this is actually going to be 0 because we have pi into, for any integer multiple of pi, sine is going to be 0. So this is 0, which means we don't even need to bother evaluating this because we know the whole thing is going to be 0 because it's multiplied by this. So now we can go here, so we can focus on this one instead. So once again, let's do the separation. So we're going to have sine phi d phi. Then this becomes 0 to pi of 1 minus cosine sine phi d phi. And then I believe this is going to become minus cosine phi minus cosine cubed phi over 3. So this is another one that we already did in a previous video. So this is going to be evaluated from 0 to pi. So let's see what we get. this is going to be minus. Okay, so at pi we have -1, then we have -1 to the power 3, which is -1, so it becomes +1/3. And then we're gonna subtract. We're gonna have 0 here, so that becomes 1 minus 1/3. And this is going to be, so we have -2 plus 1/3, which is 2 minus 1/3, which should be, so actually this is 2/3 here. Let me check. So we have this, yep, -2/3, so this should be 4/3. Okay, and then finally, let's just clear here this here. We have this integral here, which is going to be half of 1 minus cosine 2 theta d theta from 0 to 2 pi, which is half of the following. We have theta minus half of sine 2 theta, and since it's going from 0 to 2 pi, this is going to be 0 for both cases, so we're left with pi. And then the final answer, once we multiply this by that, because we know this whole thing is 0, we're going to get the flux integral of this particular vector field on that spherical surface is going to be 4 pi on 3. So that's going to be the total flux, or the total amount of field, of vector field, going through that spherical surface. So hopefully this has shown you how you can extend the same concepts from regular surface integrals to surface integrals of vector fields. And in the next few videos, we're going to continue doing some more examples just to show you how this applies to other more complicated cases.